Okay, welcome back everybody to another session. So today it's our pleasure to have Charles Bordenave from the the Institute of Mathematics, in Marseille, who will speak to us on strong asymptotic freeness for independent uniform variables on compact groups. Charles, thank you for agreeing to give this talk, and please.
Thank you very much for the invitation. Very happy to give you a talk in your nice seminar with all these math departments together. Okay, so I'm going to speak today about joint work with Benoit Collins. You can find it with, I think, roughly the same title on arXiv. Okay, so as you will see, it will be a mixture between high-dimensional phenomena, probability theory, and a little bit of representations theory. Okay, so just to put the framework, we will speak about representation in high dimension. So I remind you what is a unitary representation. So you take a compact group G, and then a unitary representation. So you consider rho will be a unitary representation. So rho of G for any group element is a unitary matrix, and it's a morphism. Okay, and for the kind of representation that we'll be interested in will be the regular representation. For example, if G is a unitary group, rho of U is just U, right? U is a matrix. Determinant of U is another representation of dimension 1. Or you can also take tensor products of your matrix, and also take tensor products of the conjugate of your matrix. And all these three elements are just unitary representation of UN. Okay. And what we would like to study is representations. So here the underlying dimension is capital N here. Okay, and what we want to study is representation. What does the representation of a compact group, like the unitary group, so of dimension small n here, okay, what do they look like in high dimension, okay, when capital N goes to infinity. So first, to state the problem properly, we will use some ideas of notions of non-commutative probability. And this idea was already present by some seminal work of Philippe Yann in the 90s. But what we will call, but our point of view is very different. So there is essentially no intersection with the work of Yann, but except that we want to use some non-commutative probability to explain some phenomena of representation theory. Okay. And okay, so first, what is a non-commutative probability space? Okay, NCPS for short. So it's a unital algebra. So it's a pair from a unital algebra. So you have a unit in your algebra, and linear functional, a trace tau, which goes from which sends the unit of your algebra to 1. And for example, the main example we think about are just the algebra is just matrices of size n, and the trace is the normalized trace. Okay. So, and we speak about star algebra, which means that they come with an involution, usually denoted by star. Okay, it's for the matrix, it's just an adjoint. Okay, so it's a linear involution, which does exactly like you may think about adjoints do for matrix groups, matrix algebra. And okay, exactly for the trace, when you take tau of A star, you want it to be the conjugate of tau of A. Okay, and we will require that our trace is positive and faithful, meaning that tau of A star is always non-negative, and there is equality if and only if A is 0. Okay, and when you have that, you can define the standard norms. The first norm, which corresponds to kind of Euclid L2 norms, which is the square root of tau of A star, and another one, which will be the analog of an infinity norm, which, okay, we forget about the infinity sign, which will just simply be, as you would do in Euclidean space, as a supremum of AB where B has L2 norm less than 1. Okay. We will encounter only two types of very simple non-commutative polarity space. The first one is just a set of algebra of matrices of dimension n, so it's a normalized trace. And the operator and the norm that you define like that is simply the operator norm. Okay. And also we'll look at the group algebras. So you take G, our group will be countable. So G, a countable group, and R, you look, it's an algebra on L2 of G, okay, small L2 of G, which is generated by the left multiplication operators, okay, which are defined like that. Lambda of G applied to a Dirac mass at H, where H is an element, where H is an element of the group, and G also is simply the multiplication on the left by G, okay. So, and lambda is also simply the left, it's a representation of the group, and it's called the left regular representation, okay? And it's a unitary representation. And when you make, so if you consider this algebra, and you take the trace, which is simply the, you take the scalar product with respect to the unit of the group, or with any other element of the group, it doesn't matter, by transitivity, then the norm that you obtain is again the operator norm on L2 of G. Okay. So for the example we'll speak about, we just, the corresponding norm that we will be interested in is just operator norm. Okay. So if you have questions, do not hesitate to stop me. Okay. Now we need another notion, which is the notion of convergence. Okay. And then we'll be able to be back to our problem of representation theory. So imagine that you have a sequence of elements. You have a sequence of non-commutative probability spaces. So here you can think of, for us, it will be Mn of C and the normalized trace, okay? And this will be simply matrices. Okay, so you have a family of D elements, okay? And you have a family of D elements, a sequence of, here you have a sequence of D elements, and here you have just D elements, which belongs to some non-commutative probability space A tau. And then you say that they converge in distribution or in non-commutative distribution if when you test your polynomial, when you test your variable against any non-commutative polynomial in T variables, the trace converge to the trace of the same polynomial, but when you replace your variable v1 to vd depending on n as the limit variable, okay? So a non-commutative polynomial is just a word, it's a weighted sum of terms of the form which are like v1, v2 star, v1, v2. It's okay, plus v2 star, v2, v2, v1, for example. This is a non-commutative polynomial, okay? And so this is convergence in distribution, and strong convergence, it's when the convergence, there is convergence in distribution, and also you have convergence of the norm. Okay, so for matrices, it will be convergence in operator norms. Okay. And when the limits v1 to vd are free, so I will not define you what does it mean, because it will be not necessary for this talk, but I will give you a picture on the next slide. Okay, so if the operators, if the elements v1 to vd are free in the algebra A tau, then one speak of strong asymptotic freeness, okay, because they converge to free random variables. So strongly is a strong convergence, and just asymptotic freeness is a convergent distribution. Okay, that's the standard, very standard vocabulary in operator algebra.
Can I ask a question?
Sure.
Why is the requirement non-commutative polynomial? Is there also a notion of commutative polynomials, I guess, right?
Yes, but okay, so a non-commutative polynomial is just a word, if you want, the word, so a non-commutative polynomial it has some abstract variable, x1 to xd, okay? And so it's just a sum of the monomial, it's a sum of monomials, and the monomials are just elements when you put in order the xi's and the stars. So if you would like to speak about commutative polynomial, the problem is that the variable xi, usually they don't commute. So if you think about matrices, okay, if you take P, AB is different, Pxy is different from Yx in general. So that's why you insist on the fact that they are non-commutative. So xy and yx are two different polynomials.
But if you have convergence in distribution, then it would also hold the convergence for any polynomial, right?
Sure. Because if you take a polynomial, then it implies, for example, that tau n of, if you take just a single element, vn to the k, converge to tau of v1 to the k, or in k. So it implies a convergence of moments, for example, for a single. But also you also want to describe the kind of joint distribution of v1 and v2. To describe that, it's not like in the commutative setting, where you just need essentially to understand the joint moments. Yeah, you need to understand the joint non-commutative moments.
I see.
So just knowing, okay, so if you just know tau n of v1 and k, v2 and l, it's not sufficient to characterize what we call the distribution of v1, v2. Because they may not, if they commute, it's sufficient, but if they don't, it's not sufficient. Okay.
Thank you.
Okay, so yes, sure.
Can you give some non-trivial examples when you have convergence?
Yeah, I will give you some. There are some, I will give you examples after that.
Okay.
But yeah, I will give you example and we comment, okay? Sorry. What happened? Okay, so I will first give you what are free elements, what are free operators. Okay, so let's look at the free group with D generators, which I denote by G1 up to GD. Okay, and they are inverse. Okay, so here I represented try to represent the Cayley group of F2. Okay, so you have two generators, G1, G2, and they're inverse. Okay. And so the free group looks like that. When you multiply on the left, you multiply by G1, on the right by G1 minus 1, and top and bottom by G2. Okay. And if you consider the left regular representation of G1 to GD, so I recall you this is a multiplication on the left by G1, and the multiplication on the left by the group elements lambda G. Okay, these guys are free. Okay, so you can write also a formal definition of what is it to be free, but you have to take a picture that freeness is related to some tree-like structure of your operators. Okay. Okay, so now you will find example of non-trivial example. Okay, so this theory has started with Niculescu in the 80s, and at the beginning he was not interested in random matrices, but in the 80s, but in the 90s he realized the connection between the free probability theory developed with the theory of random matrices. And so what he has proved, among many other things, is that if you take GUE matrices, so you take your matrix are symmetric matrices with independent Gaussian entries, complex Gaussian entries, and they are Hermitian, sorry. So these matrices, seen as families of matrices, they converge to they converge in non-commutative sense. They are asymptotic free, and they converge to free. If you take so they converge to free semicircular operators. Okay, so I will not define what is a semicircular variable, but okay, so that's an example to have in mind. It's a historical example. Closer to our topic, if you take independent, if you take matrices, unitary matrices of dimension small m, okay, And you take, okay, so you look at the unitary matrices and you consider the R measure on that, okay, and you sample independent matrices U1 up to UD, which are independent, are distributed unitary matrices. So you sample matrices, unitary matrices uniformly on the unitary group. Then Voiculescu proved that they converge, they are asymptotically free, and so they converge in their non-computative distribution. They converge to my lambda of G1 up to lambda of GD. Okay, where the G1 up to GD are the generators of the free group. Okay, so that's why Voiculescu in the late 90s, and also if you take permutation matrices, so you take a uniform matrix on Sn, and you look at its permutation matrix, and you take d independent copies of that, and it converges to lambda to the same object, lambda of G1 to lambda of G. Okay, so when I speak about a random object, it means that the convergence holds in probability or almost surely. If you want details about the statement, I can tell you this stage is okay, I think. And strong asymptotic results. So I remember you. So strong asymptotic results. It means that you want to prove that this kind of convergence for when you take any polynomial, but not simply the trace, but the operator norm. So it was much more difficult to prove statements like that. And there was a very influential paper by Agerup and Torbjörnsen, who refined the result of Voiculescu for independent Gaussian unitary matrices, and they proved the strong asymptotic freeness. Okay, by a very and they have introduced a very general method, which I will comment later on. And this paper has been generalized in many directions, but it was more, the technique is very relied a lot on the independence of the matrix entries. Okay. For unitary matrices, as a byproduct of Agerup and Torbjörnsen, Collins and Mal proved that they were also converging strongly asymptotically free. And for independent permutation matrices, uniformly distributed with Benoit, we also proved the strong asymptotic. Okay, using a completely different method, which we will see later. Okay. Now, let's come back to what I want to speak today. You take a compact group, okay, and you take a rho n to be a unitary representation of your group of dimension capital N, okay? Now, the way we will study high-dimensional representation is by taking U1 up to UD ID uniformly sampled elements of the group sampled according to the R measure on G. Okay, so these are group elements. Okay. And what we will study now, if you look at the image of the UI through your representation, you obtain a new unitary matrix of unitary matrix of dimension U of dimension capital N. Okay. And now the question is, since you have independent variable and you have a sequence, if you take a unitary representation with this dimension which goes to infinity, you may wonder about the convergence in distribution or strongly of this d-tuple of variable. Okay. So that's a very broad framework, and the objective would be to try to understand representation of classical groups in high dimension. So in this talk, we speak about the unitary group or the orthogonal group, and we'll see it's a difficult question. And we will study it in the regime where both n, small n, and capital N go to infinity. Okay. Okay, let's see. So this was our primary motivation. Another motivation, is So another motivation is to try to study non-usual R measures, okay? Because if you have a group and you look at the image of your group through your representation, you will get a subgroup of U capital N, okay? And since you sampled according to the R measure of the UI, the image is also sampled according to the R measure on the target group, on gamma N, okay? And then you may wonder exactly as Voiculescu has initiated, and to try to understand the convergence of the convergence in distribution, or the strong convergence of elements sampled independently from the R measure of a matrix group of dimension capital N. Okay, so here you look at the point of view is to try to understand R measure of relatively complicated groups of high dimension. Okay. An alternative motivation, I will not comment too much, is to try, if you want to, because I'm usually here, there is no graphs, but I like graphs. And one of the motivations, for example, from our previous work with Benoit, was to try to find nice finite dimensional approximations of pictures or operator like this one. Okay, if you can. So this is a nice, very nice drawing made by O'Donnell and Wu. And so here you have you can see that as an operator acting on a kind of it's obtained as it's nearly a free group. And so you would like to try to find finite dimensional approximations of objects like this one. And what does it mean to be a nice approximation? It could be that you are close in terms of non-commutative distribution, or you are close also in terms of operator norm, which is much more challenging. Okay, and the last motivation, I don't know anything about, but it's more Benoit, my co-author, Benoit Collins' motivation is if you consider the unitary groups or the canal group, in fact, operators like this one, well, you have a sum of so the UI are again independent elements sampled according to UN or ON. If you look at operators like this one, they have been studied in the context of what has been called the quantum expanders by Hastings and also Arrow and Pizier. Okay, so and these operators they are interesting in quantum information theory, but I cannot tell you much more about that. Okay, and you see this is an example of a representation. Okay, because as we have seen, rho of U equal to a U tensor U bar is a representation of the unitary group. Okay, so you are taking a polynomial, which is simply x plus x1 plus x2 plus xd plus x1 star plus xd star. Okay, so what you are making exactly the framework I'm speaking about, but you are interested in a very specific representation, this one, and a very simple polynomial, which is of degree 1, which is this one. Okay. So what we are trying to do completely contains some motivation in quantum information theory. Okay. Now I will tell you what we have proved in this paper that you can find on arXiv. Okay. So we start with the very convenient representation to study, and we start with this one, and we'll tell you some consequences for other representations. Okay, so we only make the result for unitary groups up to now, because we also do the orthogonal group, but essentially the same strategy. Okay, so you take the unitary group and you consider there is a representation of dimension small n power q. Okay, where q is a sum of two numbers, and the sum, it's just a tensor product representation where you take a given number of you take the tensor product of u q plus times, and you make a tensor of the tensor product of the conjugate of this matrix q minus 1 times. Okay. So this is called the tensor product representation. And if the number of times that you compose by you tensorize by u and the number of times that you tensorize by u bar, so meaning if q minus is equal to q plus, there are some fixed points of its unitary representations. Okay. Okay, meaning, for example, so meaning that there are some invariant subspace H, which are included in C power n, such that a rho of U of H is equal to H for all U in UN. Okay, so that's what they call fixed points. For example, if you take this representation, U tensor U bar, and you apply the identity matrix, you will see that it is the same thing as if you see that as a matrix acting on Cn squared, okay, because it's a matrix of size n squared. Okay, and here you identify Mn of C with e power n squared. Oh, okay, that's what I wrote. So identifying Cn squared. So if you look at how, if you apply to U bar the identity matrix, it's just the action of conjugation, and you get the identity. Okay. So we denote by H the vector subspace of C power n of fixed points. And there is a way to describe it completely. Okay. Now here is our main theorem. You take D independent copies of R distributed elements on the unitary group of dimension small n. Okay. You look at their image through the tensor product representation. You call that VI, V1, VD. And what we prove is that on the orthogonal of the fixed points, okay, then almost surely, these D elements, they are strongly asymptotically free. Okay, and as long as Q is not growing too large, so it's a representation of dimension capital N, which is of as long as Q is not too large. Okay, so like log n. Okay, so it implies that, for example, if you look at the norm of V1, V2, V1 star plus V2 square, V2 star square, if you restrict the norm, the operator norm on the orthogonal of the fixed points, then this will converge to the operator norm of lambda G1, lambda G2, lambda times lambda G2, lambda G1 minus 1 plus lambda G2 minus 1 squared. Okay? This is the consequence of that result. Okay. Some comments. So the asymptotic freeness, so just the convergence of the normalized trace, was proved by Voiculescu. I mean, it's not written in the work of Voiculescu, but it is a consequence of the work by Voiculescu and some general remarks obtained by Collins, Caudrelier, and Mal. Okay, and our result is a 0-1 law, and it tells that the only obstruction of strong asymptotic freeness are just the existence of these fixed points. Okay, and as we said, this polynomial has already been treated by previous authors using Schwinger-Dyson equations. Because our organized things are motivated by quantum information theory. Okay, so let's see some consequence of that for irreducible representation. So, I'll recall you that a representation is irreducible if it has no non-trivial stable subspace. Okay, so for example, we have seen that U times U star is reducible. Okay, because we have observed that when you compose by multiple of the identity matrix, it's stable. Okay. So there is a complete description of the irreducible representation of UN, And they are indexed by a signature, which is a pair of Young diagrams, meaning sequence of non-increasing sequence of integers. Okay, and the length of such representation is such the length of the, it's just the sum of the length of the elements of the non-increasing sequence. Okay, for example, the representation, there is a kind of vocabulary, a dictionary, which to a reducible representation gives you its signature. So for example, for the regular representation, U, the signature is just this constant sequence 1 and 0. U bar is a 0 and the constant sequence 1. The determinant of U, it's the constant sequence with n ones and 0 and so on. Okay. And the consequence for irreducible representation of the unitary group is the following. If you take independent R-distributed matrices on UN and a irreducible representation, again, I take VI, the image of my unitary matrices, my unitary elements of UN through the irreducible representation. And what is we say that these are strongly asymptotically free as long as the signature of the representation does not grow too fast. Okay, and it's a corollary of what I said, because it's a irreducible representation is always a sub-representation of a tensor representation where Q, which was equal to Q plus plus Q minus, is simply the length of the representation of the signature. Okay, and okay, so there is a comment on the size of the signature. Okay, and this log n over log n is vastly non-optimal, but there is some restriction. If you think about the very famous representation, which is just a determinant, okay, this representation, determinant of U, is one-dimensional and thus commutative. Okay, and commutative elements cannot be free. Okay, if you think about the tree picture, the fact that you have a tree comes from the fact that you have you are non-commutative. Okay, so there is some restriction, and the determinant for the determinant, the length is capital N, is small n. Okay, but so there is some threshold where above which this result is false. We don't know where is this threshold, but there is some. Maybe the determinant is the only obstruction. That's what. Okay, now it's the time remaining. I will just give you some ideas. Just put just tell you the ideas which we have used to give this proof, to build this proof. Okay, so first, as I said, the very important work of Fagerås and Torbjørnsen was I proved strong asymptotic freeness for Gaussian independent Gaussian unitary matrices. It's used on linearization, which I will comment, and some analytic properties of the Stieltjes transform. Okay, and they use some what is called Schwinger-Dyson equation in the jargon, or loop equation, that's the way a physicist calls that, and some heavy complex analysis. Okay, in our paper, in a previous paper with Benoit Collins, where we proved strong asymptotic freeness for independent random permutations, these analytical relations are not, this analytical study is not very suited to permutations. So we introduced a more combinatorial method. Okay. And what we have done in our paper, in present work, is to expand the technique that we developed for random permutation to this new setting. Okay, so I will go very quickly through the steps of the strategy, and I think some of them, like the last one, is general interest beyond random matrix theory, and okay. The other one are. Okay. So let's see. the first one is, so you have to kill, you remember you have some, the vector space of fixed points. So you fix here, you fix, you take your independent high distributed matrices, and you look at the image of your representation of your independent matrices for your representation. So you define new matrices VI in new capital big N. Okay, and you have to project on, there is some vector subspace of fixed points, okay? And so what we have to project our matrices on the orthogonal of these fixed points, okay? Because as I wrote, we want to prove the strong asymptotic freeness on the orthogonal of this fixed points vector space. Okay, because on this vector space, there is no freeness here, because again it's commutative since it's just invariant. So there is a nice lemma. So it's a lemma. Is in fact the which I found very nice, which is the probabilistic operation of centering the matrix. Okay, if you look at the expectation of the VI, okay, it's exactly the same. The expectation of the VI, it's an explicit form, and it's just the orthogonal projection onto this fixed point vector space H. Okay, so a consequence of that is that since you are interested by the restriction of your matrices on the orthogonal of H, what you simply have to do is, we use this bracket, what you simply have to do is to prove the strong asymptotic freeness of this centered matrices, okay? VI minus the expectation. Okay, so I'm a probabilist, so it's very convenient to work with centered, okay, yeah, it's matrices, but it's centered matrices, okay? So this orthogonal projection is the same as centering the matrices. Okay, so that's a very nice fact. Okay, the second nice fact is what was used by Agrup and Torbensen in their seminal paper, is that you remember, to prove strong asymptotic freeness, you need to prove the convergence along all non-commutative polynomials. And it's very complicated because you can take any word with stars and you can combine the terms in any order. It's a nightmare, especially if you want to do some analysis or some combinatorics. Okay, and here to help you, to save you, there is this what is called linearization trick. Okay, so so if you take elements, so V1 up to PD are element of my non-commutative probability space A tau. Capital, the same with capitals are, let's say, matrices. Okay, to avoid heavy notation, I define VI of I plus D to be VI star. Okay. Okay, so now I have a sum over 2D terms. Okay, and this linearization trick has many variants, and one of them is the following. What we want to prove, meaning the convergence of the operator norm of, for example, P of V1 up to P to D converge in operator norm to this, so the norm of P against the small v's, okay? It's equivalent to proving the following statement, to prove that this convergence holds for all polynomial of degree 1, but where the coefficients in front of the monomials of degree 1 are matrices. Okay, so you replace complicated non-commutative polynomials of arbitrary degree by linear polynomial of degree 1, but with matrix valued coefficients. Okay, and this looks much easier, but in fact it's equivalent. If you prove that, you prove. If you prove this, you prove that. Okay. And so this, I should have put names of, maybe because you don't see it. This was, I think I have a name below. Let's see. Yes. This was by Pizier. This was in the context of in operator algebra. This was observed by Pizier and also by Aigop and Torbjörn in their seminal paper. Okay, so our daunting task to prove convergence along of operator norms of any non-commutative matrix, of any polynomial of my matrices, boils down to just proving convergence of weighted sums. Okay, so it becomes linear, but the weights are matrix value. Okay. And they have a fixed dimension R. Okay, you have to prove that for any fixed integer R. Okay, now it's still too complicated. Okay, so so you have what you are interested in. You have your matrix. You have some free unitaries. Okay, like you can think of that as the lambda of G1, where G1 and this is lambda of GD, where the G1 and GD are the generators of the free group. Okay, these are my free unitaries. The VI are my UI tensor product Q plus tensor product UI bar Q minus. Okay, I forgot the tensor product here. And so what you want to prove, you want to prove the convergence of an operator like that. Okay, so it's as I said, it's a polynomial, matrix valued polynomial, was of degree 1. Okay. And when we have an operator like that, in fact, there is an operator which we called matrix valued non-backtracking operator. Okay, which is this matrix. Okay, so so I recall you that I star is simply I plus D and VI star. And V, so it's V of I plus D, it's VI star. Okay. So this is operation, star is operation where you go from one unitary matrix to its inverse, its conjugate, adjoint. Okay, so this operator is like, instead of, it's also linear in the VIs, okay, but it's a weighted sum, so it looks more complicated. So EIJ are the usual canonical matrix elements, okay, where only, so, but they are indexed by the generators of the free group and their inverses, okay, and this is this operator. And we call that the non-backtracking operator due to this constraint. Okay, so because this constraint is saying that in some sense, you combine VI and you combine the indices IJ if J is not has not the index corresponding to the adjoint of I. Okay, and there is a claim which is a bit loosely stated here, that if you prove the convergence of the spectral radii, so this, of all these matrices for all possible weights, okay, then it implies the convergence you want on the spectrum of A. Okay, where A is this. The way we prove that with Benoit Collins is by some extension of, there's some kind of spectral mapping formula which goes under the name of Yerabas identities, which relates, which are kind of one-to-one map between the spectrum of A and the spectrum of B. Okay, where but what I'm not telling you is the way you, for a given set of AI, you have some map which maps them to some family of the BIs. Okay, it's a little bit more complicated than that, but I skip. It's just the idea. Okay, now I will try to comment on the name non-backtracking and why should it be simpler to study this guy instead of studying this guy. Okay, the way is that if you look at the limiting object, which you can see as being the free group, the powers of B are very simple. Okay, if you take phi, which is a vector in C power R, E is unit of the free group, and delta J is just an index between 1 to D. Okay, so it's just you choose the group element, the index of one of the generators of the free group. If you take the case power of B, you apply this to this vector. What you will get is that this sum will be some phi of G that you can write down in terms of the product of the BI. So this one, I will not explain it completely. But what is interesting, that the support, it's this when you take iterates of this operator B, it will be the support is over all group elements of the free group, which are at distance, which are at a distance exactly k in the free group, in the Cayley graph associated of the in the Cayley graph of the free group. Okay, so meaning that there is a group elements, you sum over all group elements, which you can write in reduced form as a sum of k distinct as a sum of GIR1 up to GIK, where two consecutive elements are not inverse one from each other. Okay, so when you iterate inwards, so when you iterate a power of B's on the free group, what you are following is just a need. So if you look at B squared, okay, here I take the B squared, you will be concentrated on that guys. Okay, and so on. So the group elements which are distanced, where you can reach from the unit in 2 steps. Okay, so B, this non-Beckerian operator, in fact, it follows geodesics in FD. Okay, so when you take B squared, you look at distance. You look at group elements which are distance 2 from the unit element. Take B cube, distance 3, and so on. So despite it looks a bit strange at first sight, the fact that we have added this constraint, and especially this one, makes the powers of B to have a very beautiful geometric interpretation in terms of on the free group. Okay, so now comes, I will be quite fast on that. So now you have to, these are kind of general facts. Now you really have to go back to your model. The VI are the free generators. You look at this operator, and this is and you want to prove that this is the matrix you are interested in, the unitary matrix you are interested in. Okay, so here I recall you, the bracket is just your unitary matrix recentered, and the VI are again the tensor products of my. And what you want to prove is that the spectral radius of B, of these guys, converge to the spectral radius of this guy for all choice of weights BI. And BIs are of dimension R, and you want to put that for any choice of R. And the usual way to do it is to use what is called the I-trace or expected I-trace method. Okay, where you bound the spectral radius, the 2 case moment of the spectral radius, by the operator norm of B power k squared. Okay, but you can write like that. Okay, so this is the operator norm of bk squared. Okay, and then you bound the operator norm by the trace. And what you would like to prove that this is less than something that you control in terms of the spectral radius of the limiting object. Okay, and the way you do that, you use the linearity of the trace and the expectation to switch. You expand the trace as a sum over many terms. And there is a big, there are 2 ingredients to understand. There is a big combinatorial part, where you have to understand the tensor product of the VI and how will they relate to the same expression but on the free group. So I will spare you that. And another thing to understand is the probabilistic part, because where probability comes in is that these guys are random variables, so they are centered unitary matrices, random unitary matrices. you have to understand the average of products of entries of these matrices. Okay. And I will just tell you how you, because this is very, there is a way to compute for any, in fact, for any group, there is a way to express. So what we want to express is to understand, for example, an expression like that. So you have products of, you have a product of indices using your unitary matrices. Oh, okay. Here I take the orthogonal group for simplicity. You take the product of element of the matrix entries of your random matrix, okay, which is R distributed. You recenter that, okay, and then you take a product of elements like that, okay, and you want to bound an expression like that, okay. So in general, you would like to compute expectation of products of UI t, jt for t, for example, for t going. The simplest example you would like to compute is that you look at the product, you want to compute the moments, you take it, gt, which are any indices, it, jt, there are any index between 1 and small n, and you would like to understand how can you prove, can you give a formula, a meaningful formula for the expectation of products of entries of your R distributed unitary matrix. And the answer is yes, and it can be done by Weingarten formula calculus, okay, and which is an analog of what is called Wick calculus for computing quotient moments, okay. And there, as you know, Wick calculus, it allows you to compute moments of the Gaussian variable in terms of counting pairings. And here there is a more complicated formula for the unitary group, or orthogonal group, or in fact any group, which allows us to compute, to have a closed form expression, closed with bracket, for a complicated expression like this one, okay? And so I will not tell you what are these coefficients and what is the exact meaning of this formula, because my time is almost done, but there is a way to express this expectation of moments. Okay, now what we are interested is estimating this right-hand side as small n goes to infinity, okay? And also nq large, okay, because here you take, and capital T is like, should also be large. Okay, so we have a huge product. So if you want, you are kind of looking at a very high frequency, because it's a product of a huge number of random variables, but we still want a kind of sharp control for their value. Okay. And Benoit and Matsumoto, they already had a combinatorial expression for this, for not exactly this one, but for, because this one is recentered, but for a simplified version of this question. Okay. And one of the corollary of what we proved is a general, for example, a statement like that. Okay, you take Gij to be independent Gaussian random variable, IID. Okay, here you have your horrible, complicated form where you take the product of recentered entries of your R unitary matrices. Okay, so there is a scaling factor because, okay, for example, square root of n times Uij, if U is uniform on Un. This is almost, as n goes to infinity, this is very close to Gaussian random variable. Okay. So this is saying that, so this is true, this is a convergence, for example, in total variation. Okay, this was observed by Olshansky and Jiang. Okay, so here what we want to prove is not a convergence in total variation, but a convergence in LP in some sense with very high moments, okay, where P is very large. Okay, and what we can prove is that if you have less than n power less than 4 or 7 terms here, you can compare, you can show that this product, this expected product, is very close to exactly the same expression where you replace the UI by the Gaussians, okay? Up to a small offset terms, and delta and eta, which are small. Okay. And once you are here, you can use the usual big calculus to have an expression for this guy. Okay. So that's the main probabilistic part of our proof, is to use Weingarten formula to prove a kind of a very high moment estimate, of a unitary random matrices, product of entries of unitary matrices. Okay, so some conclusion. So we have seen a kind of heavy machinery, but kind of robust to prove strong asymptotic freeness for tensor product representations of unitary matrices. What we have not done is some non-asymptotic bounds. It would be nice to have some. We have not done the tensor product of permutation matrices. So the same question, but where you replace the unitary group by the symmetric group. I'm more interested also by proving a strong convergence where you have a random matrix and a deterministic matrix. Okay, but this is beyond the current reach of our method. And another very puzzling fact is what happens when small n is fixed. So the dimension of the unitary matrices you consider, the group is of dimension n fixed, for example, n equal to 2. And Q, the number of tensor products that you take, goes to infinity. Okay, but if you do that, you have very few random variables. Okay, so here it's I've made an experiment. So I take I take SUN instead, because you want to kill this to kill the commutative determinant representation. Okay, you want to, if small n is fixed, I've take independent R distribution matrices of dimension in SUN. N is here, n is relatively large, but and I take the sum of I take the tensor products of that Q times and the adjoint. Okay, so it's and in blue you have the histogram of the eigenvalue of this matrix, and in orange you can follow the theoretical curve predicted by free probability theory, and it's very sharp. Okay, and as you see, there is no outliers. There is no eigenvalue beyond that point and below that point. So that's what we prove with when n is going to infinity. And okay, but if you do n fixed and small n equal to 3, but you increase the number of tensor products. So I'm very bad at numerics, so I could be, I cannot do more than 9 tensor products. You can still see that there is no outliers beyond that point and beyond that point. Okay, but here you have only like as a Riemannian manifold, this has dimension n squared. So you have only 9 random variables here. And with 9 random variables, you create asymptotic freeness and strong asymptotic freeness. So I would love to, so it would be very interesting to prove strong asymptotic freeness where n is fixed and q goes to infinity, but it's very hard. Okay, that's what I wanted to say. Thank you for your attention. I cannot say.
Yeah. Thank you very much for this very nice talk. Are there any questions or comments? I had a question. So based on your simulations, if I understand correctly, all these can also, no, you said you don't have non-asymptotic bounds yet, right?
No.
Yeah. So you don't have rates of convergence, essentially? That's the idea here.
Yes, we don't have any rate of convergence, yes.
There is part of the method.
What?
Sorry, is there a particular part of the method that right now restricts this, or it's not clear?
There are various parts, I guess. So as I said, so the last part is very quantitative, so that's fine. The linearization trick, it's kind of, as you say, so you have a polynomial and then you have some magic formula, which instead of looking, you just look at something like that. So, and the relation between the degree of the polynomial and the, it's not very quantitative. I mean, it's an algorithmic way, but I think it would give bad, from a quantitative point of view, it's not very good. And also you have this spectral mapping formula, which goes from, you want to understand an operator like that. And what I give you is some operator like this one. It was written like this one, with IJ, which was my non-backtracking operator. And also these are kind of very formal algebraic identities, but we never try to see, to put epsilon in there. So maybe it's very tough, I don't know. So yeah, there are maybe, yeah, I don't know if this method is the best candidate for, at the moment it's the only method available. But for example, for matrices with independent entries, like if you come back to the setting of independent GUI matrices, there is a recent result by Latawa, Van Andel, and the third co-author, I forgot, where they reprove, in some sense, they prove a quantitative statement, strong convergence, a quantitative strong convergence result for sums of unitary matrices. GUI matrices. And their method is quite nice. So maybe it's possible that some of the ideas could lead to some more quantitative argument.
Thank you. Any other questions, remarks? Okay, if not, let's thank Charles again. We'll see you next week. Again, we have another talk next week. Thank you very much.